Okay, we're moving on now to Chapter 2. In this chapter, we'll be taking a look at data communications concepts. And here's a quick look at the data communications concepts that we'll be talking about during this chapter. We'll start with a brief look at the data communications architecture. That's followed by data digitization, then data transmission techniques, data communications techniques, and we'll end with error control techniques. So this slide represents the overall data communications architecture. If you look closely, you can see that we have various technologies represented here. And then later on in the various chapters that we go through, we'll be covering many of the specifics about how these technologies work. If you look to the far left, you'll see what looks to be a house, and there we have a PC then connected to an access device. The access device is connected to an access server, and then through the internet the access server gets the ability to communicate with the access server on the far right, which then connects to an access device there in the corporate office, and the access device in the corporate office is then attached to various public servers, including a web server shown in this graphic here. Now the access servers that we see there in the internet cloud, those are usually our internet service providers. So the consumer and the corporate office access devices, they need to pay for the service to get access to the internet, and usually that's done through an ISP or an internet service provider. So in a data communications network, we need to have data that is digitized. Data digitization is actually the process of transforming our human-readable characters into machine-readable code, which is known as character encoding. So our characters, like letters of our alphabet, are turned into a series of ones and zeros, also known as bits. And if we group 8 bits together, we have a byte, also known as an octet. The most commonly used standards for character encoding are ASCII, EBCDIC, and most commonly these days, Unicode. The original character encoding scheme that was used in data communications was known as 7-bit ASCII. That's because it used a grouping of 7 bits. And so we're looking at an ASCII table here on your screen, and it's organized by the individual bits. So you can see at the very top of this table on the left it says MSB. That stands for most significant bit. And so what we're referring to then is the leftmost bit. If you were to look at 7 bits horizontally all in a row, the leftmost bit would be bit number 6, followed by bit number 5, and then bit number 4. So bit number 6, 5, and 4 are grouped into this grouping known as the most significant bits, and then the remaining 4 bits are down below on the left hand side of the table there, and that's the LSBs, or the least significant bits. And so that one works backwards from 3 to 2 to 1 to 0. So again, if you're looking at a string of 7 bits left to right, it's bit 6, 5, 4, 3, 2, 1, and 0 for a total of 7 bits. Now the conversion from a binary value, the zeros and ones, to a decimal value is really what we're seeing here in this table. They don't have the decimal values listed. In fact, if you go to the resources page that I've provided for you on the course menu there, and then you click on the documents link, I have another ASCII table for you there. That one does have the binary to decimal conversion values as well as showing the individual characters. So let's just focus on this example for the moment. You'll see that the capital letter A on your keyboard is represented by a 1, 0, 0, followed by a 0, 0, 0, 1. So again, I'm just reading those in the order of the bits. Starting at bit 6, it's a 1, bit 5, it's a 0, bit 4, it's a 0, 3 is 0, 2 is 0, 1 is 0, and then finally bit 0 is a 1. So in the encoding process, when you press a letter on the keyboard, what's happening is that letter, the fact that you pressed a key, is being represented by a string of 7 bits when we're using ASCII. And again, modern day we use Unicode, which is a 16-bit format, so it allows for larger alphabets like Asian alphabets, which have thousands of characters that need to be represented. But this original 7-bit ASCII, it sufficed for early computing, which mainly was English language based. And so again, it's just basically a translation of the letter you're pressing on the keyboard into a string of 7 bits that then uniquely represents that letter that you pressed on the keyboard, and then those bits are all strung together and streamed out then onto the data network, or stored in memory on your computer, or written to a hard drive for permanent storage. And so, as we said in the previous slide, there's 3 different methods: ASCII, EBCDIC, and now Unicode. And ASCII was the first character encoding method to be used. So this slide then just shows you the EBCDIC character encoding table, and it works just the same way that the ASCII table did. It's just that there's a different numbering scheme that's applied to the letters, the characters that are used here. In the previous slide I was talking about the capital letter A, and I did fail to mention that there are some other codes here. Like you'll see that in pink the LF is highlighted here, which is line feed. So that's how the computer knows, or like when you're Microsoft Word and you have a line of text and then you want to move down a line and have a next line of text, so a line feed gets generated in that particular case. So these characters that you see over to the left portion of this table here, those are all representing different types of functions basically that are pretty standard within most computer environments. If you look down towards the very bottom on the left, you'll see a CR, which stands for carriage return. You'll see ACK for acknowledgement. And so again, those are pretty common in most computer data communications environments. Now this particular table, the EBCDIC table encoding scheme, was used primarily on IBM mainframe, so you probably won't run into this while you're working out there in the IT field, unless you happen to work someplace where they've got a lot of old equipment that might include an IBM mainframe, or maybe some very early IBM equipment. But this was pretty much relegated to exclusively the early IBM environment. Now here is a representation of the Unicode table. We can't really show you the entire Unicode table, which is 65,536 characters, but Unicode is an ISO standard. Remember that the OSI model that you're learning is also an ISO standard, and so this particular ISO standard is 10646. That represents Unicode, so it's an open standard, meaning that all manufacturers support it. And it is 16 bits now being used to represent all of the possible characters. Again, 65,536 possible characters. The graphic that you see here is the character map that is an accessory that comes with the Windows operating system. And so if you were to click on your Start menu and then open up the Accessories folder, inside of there you should see another folder called System Tools. And inside of the Systems Tool folder is where you'll find the character map. And the character map's really cool because you can select all the different fonts that you have installed on your system, and you can identify the character set that makes up the font. By scrolling through the list here, you can see all of the different characters that are included in that particular font. And then as you click on a character, like here I've clicked on the letter A, you can see it brings it forward and makes it a little bit larger on the screen and shows you that's the selected letter. And then if you look down at the very bottom of this dialog box, you'll see there's the Unicode value, which is 0041 for the capital letter A. And that's exactly the same value that we saw in the ASCII table. The only difference is in the ASCII table, it gets converted to a decimal value, which is 65. In the computer and the data communications, it's always bits. It's always zeros and ones. But the characters normally in the table format of an ASCII table can be translated into a decimal value. So capital letter A is 65 in decimal. And what you see there at the bottom of this dialog box where it says U, which is the Unicode value, is actually being represented in hexadecimal value. This is a base 16. So the way that that works is that the very far right column, there's 4 columns of numbers here. If you look at that value, 0, 0, 4, 1, the far right-hand column then is where the number 1 is located. Well, just like in a decimal system, the far right column is the ones column. So whatever the number is in that far right column, we read it as a 1 or a 2 or a 3 or a 4 or a 5. In other words, you take that value and you multiply it times 1. So 1 times 1 is 1, right? It doesn't take a rocket scientist to figure that one out. But then we move one column over to the left, we have the value of 4. Now if that was in the decimal system, that would be in the tens column. We'd multiply 4 times 10, and so we get 40. We'd add that then to the 1 in the first column, so we'd have 41 if that was a decimal value. But this is a hexadecimal value, base 16, and what that means is the second column, instead of that value being a 10, the value is a 16. That's what hexadecimal stands for, is base 16. So we take 4 times 16, and you get 64. Add the 1 in the first column, and you have 65. So the end result, the numeric value of the capital letter A, is still 65 in both systems. It's just different ways of representing that numeric value. The computer, the data communication system, is going to represent it in zeros and ones, in bits, a binary numeric system. And many times computer programmers use hexadecimal values. And of course, the system that most of us are used to is the Dewey Decimal System, the one that we grew up with and learned in grade school. So those are the 3 basic numbering systems that you should be familiar with as an IT professional: binary, decimal, and hexadecimal. But I kind of got off track there a little bit. The main thing I wanted you to see here is just a representation of the Unicode character encoding format, and give you a little bit of information there: 16 bits, 65,536 characters, and the fact that it's an ISO standard, meaning it's an open standard supported by all manufacturers. So once we have our characters encoded into bits inside of the computer, it uses primarily a parallel system. The motherboard has circuits that are all aligned in parallel, usually in groupings of 8 bits, or 1 byte as we talked about earlier. And then we need to convert that usually over into serial format to get it out onto the data communications media. So like in the early days, we'd actually use the serial port on the back of the computer, and that attached to a serial cable. These days we use like a Cat5 cable, which is also a serial cable. And so the idea is that we need to then take this sequence of 8 bits and then organize them into a stream that can be placed onto the serial media that we're transmitting our communication on. If you take a look at the right of this graphic here, you'll notice that it says that the circuit consists of 8 copper wires, and so again that kind of depends on the particular environment that we're in. That's generally going to be inside of the computer through the motherboard. If you think about how your hard drive hooks to the motherboard, it uses a ribbon cable, which is a parallel cable. There was a time when printers were hooked up to computers using parallel cables as well. Most data communications, though, always occurs over a serial cable, meaning it's a single copper wire, or in the case of fiber optics, a single fiber optic cable that we are transmitting the data over. So that's a very important concept, obviously, to understand in data communications, the difference between serial communications and parallel communications. In this slide, we see a comparison now between the serial transmission and parallel transmission. And if you look at the columns there, the column on the left, we have several rows. First is the transmission description. So for serial, the transmission description is one bit after another, one at a time, in a series or a stream. And then for parallel transmission, it's all bits in a single character being transmitted simultaneously. You remember from the previous graphic we showed you that using 8 copper wires was the example there. And by the way, the reason they use 8 bits there too, if you remember the ASCII was originally 7 bits. When we get later on to talking about asynchronous communications, we'll show you that there used to be an added bit. So we take the 7 original bits representing the character, and then they would add a bit to represent the beginning or the end of a character, which were known as the start and the stop bits. But that can be represented by 1 bit added to that original 7. So 8 became kind of a standardized method of organization as far as the bits go. So anyway, back to our table here. Comparative speed, you can see that serial is much slower than is parallel. It makes more sense if you could send 8 bits all at once instead of having to follow each other in serial fashion. It's going to be faster through parallel. However, serial can go much further than can parallel, and so that's one of the reasons that we use serial communications or transmission in data communications, is because the distance usually is greater that we have to travel. And then the application for serial is generally between 2 computers, 2 external devices like routers, between a local area network and a wide area network. And then parallel is usually within the computer, as I had said earlier, used within your bus, and also on the hard drive controller, between the hard drive and the hard drive controller. And then also there was a time when we had printers that were also attached and utilized the parallel transmission method to communicate or receive communications from the computer. And then the cable description. In a serial cable, of course, all bits are traveling down a single wire, 1 bit at a time. And then again in parallel transmission, each bit is going to travel down its own wire simultaneously along with all the other bits. So this graphic here now shows you that comparison between synchronous and asynchronous transmission over a serial line. The top graphic is asynchronous transmission. This is a much cheaper technique to manufacture, and so you've found it quite a bit in early modems. The big advantage that it has is we don't have to actually synchronize the 2 devices. So the device on the left, the modem here on the left, is sending bit by bit the information that it wants to have received by the modem on the far right there. And you'll notice that the white box represents what's called a start bit, and the red box represents a stop bit with our 7 bits of data, 7 bits of ASCII data there in between. And so in this graphic we're actually seeing 1, 2, 3, 4 bits, 4 characters being transmitted, 7 bits each. So the 2 devices know where the character begins and where the character ends based on the start bit and the stop bit. So if you look on the right, that same graphic now, the text on the right where it talks about the efficiency, it goes through the mathematics here. We have 1 start bit and 1 stop bit for each of the bytes that we're trying to transmit, characters. So you take 2 times, say, 1,000 bytes that we're transmitting, so you'd have 2,000 control bits over the same time frame that we would be also communicating 7 bits times 1,000, or 7,000 data bits. So a total of 9,000 bits needed to be transmitted just to communicate 7,000 characters essentially. So if you take 7,000 divided by 9,000, you can see we have an efficiency rate of 77.7 in an asynchronous transmission method. Now in a synchronous transmission method, it's going to be more efficient, but it's costlier to produce because we have to add an additional component into these devices so that they can synchronize the timing between each of them. So timing is very important in synchronous transmissions because that's what will affect where the beginning and the ending of blocks of data are going to be. So again, if you look at the efficiency value over on the right underneath the bottom graphic there, we have in this case 48 total control bits per block using a protocol called HDLC at the data link layer. And so if we have 48 control bits per block, then we're only using 48 bits for that block, but within that block we're able to communicate 7,000 bits of data. So again, we take the number of characters, 7,000, divided by the total number of bits that we needed to transmit those characters, 7,048, and you can see that we're at 99.3% efficiency rate. So obviously much more efficient to use synchronous transmission, which is why your DSL modems and cable modems are much faster than the old telephone modems that we used to use. Another important concept in data communications is understanding the difference between half and full duplex. When two devices are communicating with each other, there's bidirectional communication. One device sends and the other device receives, and then that device sends a response back and the originating device receives that. So the whole issue is whether we do that in a series like I just described, or whether that's happening simultaneously. And so that's really the difference between half and full duplex. So in a full duplex environment, communication is going to happen at the same time, meaning that the device that's sending can also receive from the other device at the same time that it's sending. So it can transmit and receive at the same time. In a half duplex environment, one device is going to send, and then once the line is clear, then the other device, the second device, will respond back. If you think about how walkie-talkies work, that's a good example of a half duplex environment. Only one person can speak at a time. In modern day communications and modern day networks, we usually have full duplex, meaning that the devices are capable of sending and receiving simultaneously. The next thing we take a look at is modulation versus demodulation. We've now got our character information encoded, and it's in a series of zeros and ones. It's in a digitized format, and in the old system we had to take that digital information and we had to convert it then into sound waves to be able to put it onto the telephone wires that were going to carry it to its destination. And that's how modems came about. A modem would take the digital signal from the computer and it would actually convert it into analog sound waves and send it on its journey. At the receiving end then, the modem would take in the analog sound waves and convert it back to the digital format. So when you take those two words, modulation is the process of taking the digital and converting it to analog, that's modulation. Combine that with the word demodulation, which is taking the analog signal and converting it back to digital, demodulation. So modulation and demodulation, we put them together and we've got the word modem. This graphic then illustrates that concept of having our digital data from the PC being converted by our modem or our access device into an analog signal that is then placed onto and transported over the carrier waves of the public switch telephone network, the PSTN, and then at the receiving end taking that analog signal, converting it back into digital, and then handing it off to the PC on the right. So once our digital data is converted to analog data, it is added to the carrier wave, which is the neutral or normal wave value that's occurring within the transmedia transmission system that we're placing it onto. So there's three different ways that we can modify a sound wave in order to represent whether it's a 0 or a 1 that we're attempting to transmit. So we can adjust the amplitude, which is the height of the sound wave. We can adjust the frequency, which is how long that sound wave is, or the width or distance between recurring sound waves. And then we can also adjust the phase. If you look very closely at any individual wave, which is the sine curve that you see between the two red lines, that's a single wave. The kind of S shape that you see is referred to as the phase of the wave. And so we can actually apply voltage to the signal and change that flow so that that S curve kind of no longer looks like an S curve. We can change it to a W, and down the road we'll show you a graphic that represents that a little bit better visually for you. So here is amplitude modulation. If you look closely at the graphic, you'll see that both the frequency and the phase are consistent, but what's being modified is the height of the sine wave. And so when that height changes, that indicates that we're transmitting a value of a 1. When the height does not change, and that indicates that we're sending a value of a 0. So the receiving device is going to be synchronized with the sending device and know how long each wave is, what the frequency is, and so it counts based on that timing, and every time it sees a change in the wave, it says, okay, I've just received a 1. If it doesn't see any change in the wave, then based on that timing frequency, it'll be able to count the number of zeros that are occurring. So the proper name for one signaling event is known as a baud. And so in this particular case, any one of those sine waves would represent one baud. In fact, modems, as we'll talk about here in a little bit, used to be the speed was based on the number of bauds that it could transmit per second. And that was a one-to-one translation. The number of bauds also represented then the number of bits per second that could be transmitted. Now this graphic depicts frequency modulation, also known as frequency shift keying, or FSK. So here the amplitude, the height of the wave, remains the same, and the phase again remains the same, but we'll notice that the frequency, the distance between the waves, is what is being modified here. As you can see, the very first spacing here is showing a change in the frequency. So in this case, the change in the frequency is representing the 1. When the frequency doesn't change, then it's representing the 0. And again, at the very end there, we see a frequency change. So again, a representation of a 1. And then finally, our third method of modifying a sound wave is phase modulation. So this time the frequency and the amplitude remain the same, but you'll see what's happening here is that by applying voltage to the analog signal, we can actually affect the flow of this sine wave. So take a look at this second bar here. You have the 1 in the first position as a normal sine wave, and then notice that in the second position the dashed line is representing the path that the sine wave normally would follow, but by applying voltage that has made a change there, so now the sine wave is following an exact opposite path. It's 180 of what it used to be. So in this case here, the original sine wave was a 1. When there was a change to it, it was a 0. And as long as there's no change after that, then it continues to be a 0 until another change occurs, and then it's representing 1s at that point. So again, phase shifting is modifying the path that the sound wave would normally take. Again, watch or take a look at the gray dashes and see that's the path, the pattern that the sound wave would normally follow based on the previous wave, but by phase shifting we can indicate a change, or we can actually affect a physical change within that sound wave, which then tells the receiving system to either switch to a 0 or switch to a 1, the opposite of what it was in the previous wave. Now, phase shifting is interesting because we can actually modify it in more than one way. The first example that we saw on the previous slide and the top example here in this slide just simply shows that we can have a normal wave, which is the 0 phase shift, and that represents a 0 bit, and then by going to the 180 degree phase shift, that represents a 1 bit. But since we can actually change the phase shifting in a 360 degree pattern, we can have a 0, a 90, a 180, and a 270 degree shift reflected, and that's referred to as quadrature phase shift keying. And so now we can actually represent more bits in a single baud. So if you take a look at the bottom graphic, you'll see that if we have no change, no shift, no phase shift, then we're representing 2 bits, the pattern of a 0, 0. If we create a 90 degree phase shift, that's going to represent 2 bits, a 0 and a 1. If we have a 180 degree phase shift, that's going to represent a 1 and a 0. And then if we have a 270 degree phase shift, that'll represent a 1 and a 1. So now we have 4 different bit patterns that we can represent within a single baud. So now we can communicate more information in the same transmission time. So this is how manufacturers then began to make modems work faster. There basically are 2 ways in which we can have a modem transmit data faster. So remember that the baud rate is the actual signaling rate of the device, and they can only increase that baud rate to a certain point. But if we can come up with clever techniques to represent more bits within each of those baud rates, then that also will help us to increase the speed of the data transmission. So this slide here just tells you about the 2 different ways to do that. You can either increase the signaling events per second, which is increasing the baud rate, or you can find a way for the modem to interpret more than 1 bit per baud, as we saw in the last example with the quadrature phase shift keying. This graphic actually just represents the same information that we conveyed to you 2 slides ago. This is called differential quadrature phase shift keying, and it's just representing the 4 phases that we talked about earlier. So remember that if we have a 0 shift, it's going to represent 2 bits of a 0, 0 pattern. 90 degrees is a 0, 1, 180 degrees is a 1, 0, 270 degrees is a 1, 1. And so they're just showing you the different patterns here about what a 180 phase shift, a 0 phase shift, and a 270 degree phase shift looks like. And so again, the point is that we're trying to communicate more information within a single baud, and that's what we're doing here. Now we're representing 2 bits of information per baud, whereas previously the frequency and amplitude adjustment methods were only representing 1 bit per baud. And we can even take that a step further now. We can combine both phase shifting with the modification of the amplitude of the sound wave as well. So we maintain the frequency the same. That's going to be consistent, but what's going to change is the amplitude and the phase shift. And what that allows us to do then is to communicate 4 bits per baud, as is represented here in this graphic. Another way of increasing the amount of data that we can transmit over a fixed baud rate is by the use of data compression. So in this case, the sending device actually is not sending all of the bits necessary for the entire communications. Many times these compression utilities will look for patterns, streams of zeros and ones that match a certain pattern, and then they'll replace that with a special code that represents that pattern. and so we can actually represent then more information within the data stream that's being transmitted. Now it's important that both ends of the communication process in this case support that same data compression technology. So if it's compressed on the sending end, it has to be deciphered and comprehended on the receiving end, and the only way it can do that is by having the same kind of data compression technology working on that end as well. So again, the key elements of data compression are that the sending device is replacing strings of repeating character patterns with some sort of a special code that represents that pattern. The code is significantly smaller than the pattern that it's representing, so we're actually sending fewer bits but still communicating lots of information to the destination. So this is resulting obviously in the amount of data that's being sent between the sending device and the receiving device to be increased dramatically. In fact, as your book tells you, some cases, optimal cases, up to as much as 400%. Now, before we can send all these bits out onto the media, they need to be organized in a predetermined structure through a process that's known as packetization. So packetization is just simply the process of dividing the data stream that's flowing between the devices into structured blocks known as packets. So a packet is a group of bits that are organized into a predetermined, structured manner consisting of a piece of the data stream to which management information is going to be added. We usually refer to those as headers. In the case of the data link layer, we add a header as well as a trailer. So here's an example of a stream of data that's being divided into 3 packets, and you'll notice then that each packet gets its own header that's added to it. That's the management information that we were talking about. So this is very generic in its description at this point. It's not specific to any one network architecture or network layer protocol, but you'll see that there's a source address where it's being sent from and a destination address where it needs to go to. There's also a sequence number so that we can identify all these packets go back together. And then there's also some error checking information because we want to make sure that when the recipient receives the packet that it hasn't been corrupted in the transmission process. So as you're learning data communications, a lot of what you need to understand is these different structures that exist out there, which are in the form of network architectures. For instance, Ethernet has a maximum transmission unit, meaning the maximum number of bytes that it can transmit of 1,518 bytes. And then we've got at the network layer, we've got TCP/IP and IPX/SPX and other protocols of that nature. So the protocols themselves have this predetermined structure. And so what's happening is the sending device is using, let's say, TCP/IP at the network layer. So at the receiving end, as long as that device is using TCP/IP, it can understand the information that's placed in the network layer header because it understands how many bits are in each portion of that header and what the information is that's being conveyed in each portion of that header, like the source address, the destination address, and all that information that we saw there on the previous slide. So it's very important that the two devices can interpret this packetization, and they do so by using the same network architectures and or protocols to again understand that whole encapsulation process, understanding what the sequence of numbers means in the transmission. This is really where then the OSI model comes in. The sending device is going to start at the top of the OSI model at the 7th layer, the application layer, and it's going to receive some data from some sort of a program on an application like Word or Excel, and well, let's just say we're using a web browser. So a web browser calls on the HTTP API that's operating at the application layer and hands off some data to it. So that layer, the application layer, now is going to add its header onto that data. So it's beginning the packetizing process, and so this is actually going through what we call encapsulation. So as we encapsulate the data, we're handing that data down layer by layer through the OSI model, and each layer of the OSI model then, depending on the type of communication that we're going to be creating here, each layer is going to add its own amount of information, its own header. So that's the encapsulation portion, taking that original message, adding a header at each layer as we pass it down from the application layer to the presentation layer, the session layer, transport layer, network layer, and down to the data link layer where it actually frames the data, and then at the physical layer gets converted over to zeros and ones and electrical signals or optical signals and put out onto the media. Then at the receiving end is going to take that frame that it received and it's going to de-encapsulate it. So we're going back up the OSI layer at that point. So now the physical layer receives the electrical impulses or the light impulses from the media, and so now it hands it up to the data link layer. The data link layer is going to organize that into the frame again, and then it's going to read the data link layer's header and trailer information, and then it takes that information away and hands that up to the next layer, which is the network layer, and the network layer is going to read the header that was encapsulated on the sending device, and it strips that header away and hands it up to the next layer, the transport layer, and on and on. And so eventually that gets up to the receiving application on the receiving end there, that's just left with the message that needs to be processed by the receiving application. So this is a good visual then that shows you what we were just talking about in the previous slide, that whole encapsulation, de-encapsulation process using the OSI model. So on the left-hand column is our client computer, the one that's going to do the sending, using its front-end application as they have here. Again, the web browser would be a good example of that. And so it takes the information that the web browser wants to communicate to the server on the right-hand side there, and it hands it down to the application layer, and you can see then it adds a header. That's what the AH represents in the graphic there, that white box in the application layer in the left-hand column. That's the application header that's being added to the data that was handed down to it from the application program, the web browser that's running on the client system there. So now that application header has encapsulated the data at the application layer. So now that with the application header with the data, the actual original data gets handed down to the presentation layer, and now another step of the encapsulation process is occurring. Now we add the presentation layer header, and then the presentation layer header and the application layer header and the original data gets sent down to the session layer. At the session layer now we add on the session layer header. Then we pass all that down to the transport layer. It adds its header. Pass that down to the network layer. It adds its header. And then finally we get it down to the data link layer. And at the data link layer you'll see that there's both a header and a trailer on the right hand side there, the DLT that you see, the data link trailer that's being added. And then at the physical layer it's just it's not a message anymore. It's not a packet anymore. It's just a stream of zeros and ones that then get converted into light or electricity and put onto the media to get to the destination. At the destination we take those bits, we organize them into a frame, pass it up to the data link layer. Data link layer strips away the header and the trailer. Of course it reads and processes the header and the trailer and acts accordingly, and so then strips them away, hands it up to the next layer, the network layer. The network layer then processes the incoming information based on whatever information is contained in the network layer header. Once that's done, it strips it away, hands the remaining portion up to the transport layer. Again, that layer processes accordingly based on the header, strips the header away, hands it up to the next layer until we get up to the application layer, and finally it strips away that last header and hands the original data off to the server that will then perform some sort of processing on that message. Another important data communications technique is multiplexing. There are three types of multiplexing: frequency division multiplexing, time division multiplexing, and statistical time division multiplexing. And that would be in copper-based environments. In optical-based environments, we also have wavelength division multiplexing, or WDM. So this graphic is a good illustration of how multiplexing works. You can see they're taking in the first frame at the top there of the graphic several packages and then placing them into a truck in the second frame. So the idea is that we're taking many individual messages and we're putting them into a larger container, the truck, and then that truck is going to travel over the serial bandwidth, so to speak, to get to its destination. And then once it gets to its destination, then we can distribute the individual messages to their final destinations, each a separate destination. So that's very much what multiplexing is all about. You've got all of the local loops coming in from the households and the businesses to the central office at the telephone company, and then the telephone company is going to take all those incoming messages and put them onto this big bandwidth, this big pipeline that is going to connect to the inter-exchange carrier, and the inter-exchange carrier also is going to have a big pipeline where it's going to go from one pop in one location, one LATA, to another pop in another LATA, and then they'll hand it off to the central office, and the central office then is going to divide up the individual messages and get them to each individual final destination. So with frequency division multiplexing, we'll take a look at each of these actually individually in the next few slides here, but it's very much like cable television. If you think about how TV and cable TV operated for many years before they went digital, each individual station had its own frequency. Same way with radio, your AM radio and your FM radio. Each individual radio station has a frequency. That frequency represents that carrier wave. That's the known entity, the normal value of the analog wave, as far as in the case of frequency modulation, as far as its wavelength, that's consistently the same for whatever frequency you tune to. And so what you're really telling your radio receiver to do is to listen for this specified frequency of analog waves to be coming in, and then the radio receiver will say, well, anything that's above and beyond that regular frequency, or as the frequency is altered, I should say, from the normal frequency you've told me to look for, that's what's going to be converted into the sound that then comes out your speakers. So that's another good analogy, is to think of that for frequency division multiplexing. But we'll take a look at that a little bit more in the next slide here. So this graphic is to illustrate frequency division multiplexing. In this case here, we've got two different devices: a computer that wants to place data into the network or into the phone system, and then the phone that wants to put a voice communication into the system. So in this case here, the two devices are going into a frequency division multiplexer, an FDM, and the two signals get multiplexed onto a single local loop, and that single local loop then is carrying these multiple frequencies to another frequency division multiplexer. So now it's going to be demultiplexed on the right hand side there, in other words split back into its original components and then sent off to their final destination, computer getting to the internet and the phone communication getting to the public switch telephone network. So down below there you can see what's going on inside of the local loop. There's the 4 kilohertz of bandwidth that's being used for the voice signal, and there are it looks like 1100 kilohertz that's being used for the data signal, and then there's a buffer zone between the two signal, and that's called a guard band. So in case the voice signal goes a little bit beyond 4 kilohertz, its designated frequency, or in case the data signal goes along a little bit above its designated frequency, then they've got this 25 kilohertz guard band in between the two, so that they won't overlap each other. they'll just go into the guard band area. And so at the very bottom of that graphic you can see the illustration, the gray representing the slower frequency, which is the voice communication, and then the red representing the higher frequency, which is not a good illustration if you think about it. They actually put the text in red. They actually got, yeah, they got the colors backwards there. I'd never noticed that before. Because 4 kilohertz is a larger bandwidth than 1100 kilohertz, isn't it? Yeah, because you got more cycles per second. So, yeah, not a good illustration. But you can see the separation. That's the main thing they wanted you to see there. So here's a time division multiplexer, an interesting device. It essentially samples each channel that it is receiving. So we have 4 channels here, 1, 2, 3, and 4. And it brings it into a buffer, so just in case there's more data coming in from the channel, then it can put onto the serial line on the right there. Then it can buffer it, you know, so that nothing gets lost. But essentially what it does is it gives a certain amount of time to each individual channel there. So it goes to channel 1 and it says, okay, for a minute I'll receive input from you, and then it moves on to channel 2, says, okay, I'll receive input from you for a minute, and then 3 a minute, and 4 a minute. And you can see then it serializes them then onto the composite channel there on the right hand side. So this is, you know, a bigger bandwidth on the right hand side, and each little minute is represented by a time slice there in that composite channel. And of course it just keeps cycling through. It starts from 1, goes to 2, 3, 4, back to 1, 2, 3, 4, back to 1, 2, 3, 4. It just, you know, keeps cycling around. And again, you can kind of see that represented in the composite channel on the right. There's 2 groupings of an assembled frame there. So the frame on the telecommunication system can hold much more data. So it's bringing in individual frames from channels 1, 2, 3, and 4, putting them into this larger frame, and then putting them out onto the composite channel there. Now the problem though with time division multiplexing is that each individual channel is pre-assigned a time slot. So even if one is not transmitting data, it still gets a minute's worth of time slot there in the composite channel. So if any one of those channels aren't transmitting data, then you can see that that's not the most efficient use really of that composite channel, because from the telecommunications perspective they want to use up that entire bandwidth 100% of the time if they can, because, you know, that's how they make their money. So time division multiplexing is a good multiplexing technique, but it's not the most efficient. And so that's why we'll see in the next slide that we'll be using time division, statistical time division multiplexing, which takes care of that problem. So here is statistical time division multiplexing, STDM, and you can see in this example now it has an intelligent microprocessor, so it recognizes whether or not it's receiving data from any of the individual channels. So in this case, channel 1 is idle and channel 3 are idle. 2 is active but not quite as active as 4. And so based on that, the microprocessor allocates the time on the serial side, on the right hand side there, the composite frame. It takes more data in from 4 than it does from 2, and it takes no data in from channel 1 or channel 3. So now the telecommunication system is being very efficient. It's utilizing its bandwidth, its larger trunk line there on the right hand side at 100%, and it's not wasting time slots for devices or lines that aren't sending any data at all. Much more efficient way than just time division multiplexing. The next telecommunications, or I should say data communications technique that we're going to be looking at is switching. And there's 2 types of switching, circuit switching and packet switching. So the graphic at the top here is circuit switching, where we have a circuit between 2 devices and only those 2 devices can use that circuit. Telephone conversation was a good example of that before they got into packet switching on the telephone network. Before the telephone network went digital, back in the old analog days, you pick up the phone on your end and you would be connected to the destination, and you and the person you're speaking to on the other end were the only two entities that could use that circuit at that point in time. Even if you both just left your phone sets off the hook there, and weren't talking, that circuit would still be tied up even though it wasn't in use. And so then, like I say, the other type of switching is packet switching, which is a more efficient way of forwarding data from point A to point B. And so we'll look at each of those individually now in the next couple of slides. So here we are at circuit switching. It says that the work to create that signal path between point A and point B is done up front. So when you dial up a telephone and you're trying to communicate with the phone on the other end, that path between your phone and that phone is set up before the actual conversation begins to occur. Communication takes place just as if the temporary circuit were a permanent direct connection. Obviously, you're not always, of course, some people these days, I'm not sure, maybe they always are as much as I see them on the phone. But generally speaking, they're not always on the phone 100% of the time to the same person at least, right? So that circuit's not a dedicated circuit. The switched dedicated circuit makes it appear to the user of the circuit as if a wire has been run directly between the two communicating devices. It's one of the examples that I was told once about circuit switching and the disadvantages of circuit switching is if you think about the Highway 15 between here and Las Vegas, circuit switching, the example would be that you would reserve that entire roadway for yourself to drive from here to Las Vegas, and nobody else could use it while you're on the road. And then once you got to Vegas, then somebody else could use, that circuit, that pathway. So that always stuck with me as a good example of the disadvantage of circuit switching. So packet switching networks are the way that most all networks operate these days. If you remember back to our earlier slides when we were talking about packetization and taking messages and breaking them down into smaller chunks. So now that we're not on these analog systems, now that everything is pretty much digital, that means that everything can be packetized, made into small chunks of data. And so then those packets can travel over the wire one at a time. They're still going to be serialized, but the advantage we have is that they can take many different paths because that's what's available in the this large digital network that we have set up these days. It doesn't have to be one dedicated circuit from point A to point B. The path itself unknown to the end user, and a series of packet switches pass the packets among themselves as it travels from the source to the destination. So if you go back to that previous graphic, there was a packet switch cloud, so to speak, in there. It had a few switches all interconnected, and you just imagine the packets traveling any direction to get from point A to point B, which is essentially how the internet works, and in most packet switch networks. All packet switch networks, actually, for that matter. Well, here we have a visual to again cover that same concept, circuit switching versus packet switching. And so the top graphic is circuit switching. We've got either voice communications or data communications. In the case of the data communications, back when we were using modems, remember that was not 100% digital. The digital data from the computer was converted by the modem into an analog signal and then put into the analog phone network. So there was a circuit then that was established between the central office that we connected to with our modem to the other central office on the other end of the communication process where we were trying to connect to. So really a better graphic here should have shown you a central office on the left and a central office on the right with the circuit connection between the two central offices, you know, occurring in between there. So anyways, it's a dedicated path, or once it's set up, it's a dedicated path. It's only in use by the device that's attached to that path. And so not the most efficient use of the circuits that exist out there. And there's a lot of circuits. If you go down to the bottom graphic now, each one of these in this kind of pink cloud in the very center of the graphic at the bottom, what we have is the switches here. And each switch is connected to another switch by a dedicated circuit. So those are dedicated circuits. But the advantage we have now is we kind of take a step back from that cloud and we see the components that are attached to it and kind of follow the pathways. You'll see it's much more efficient. So on the left-hand side of the bottom graphic, and again we're looking at packet switching now, we take the data and we convert it into digital data by use of a packet assembler disassembler, a very generic type of device. Depends on the network that you're on, how they actually refer to this packet assembler disassembler. For instance, a frame relay network calls this a frame relay assembler disassembler, or a FRAD. So PAD is kind of this real generic type of device. But anyway, the pad then puts its data into this first switch on the left. Now that switch has several pathways that it can forward the information out of. So if, say, the top switch is kind of congested with other traffic at this point in time, then it can use its middle path, or it can use the path that's down at the bottom there. So it's much more flexible as far as the pathways. We don't have to have one dedicated circuit, and because again it's digital, if you think back to the multiplexing that we talked about earlier, we can put lots of messages onto those same pathways. So you've got all these different businesses and all these different houses that all are sending the same messages over these digital circuits, and so it's much more efficient. We're using 100% of the bandwidth, and we're able to handle congestion in a very flexible manner. And so packet switching is pretty much how you see most data networks set up today, because most everything is done in a digital fashion. Here's a little closer look now at an actual packet, or you can also call it a datagram, being transported across a packet switch network. So the top left there, we've got a data where somebody's typed in datacom is fun. So that's the message now that we're sending. And of course it gets assembled by the pad, gets put onto the local loop, and you can see now what they're showing you is the fact that it's been divided into packets, or divided into datagrams with these headers put on there. So it took each word and it put a header. So the SA, remember, is source address, and the DA is destination address, and the N is the actual sequence number, so that we know how to put the whole message back together in the right order. So we essentially have 4 different datagrams here. If you look at the top graphic, and the words that's on that pipeline, and you see above it, it says data, and then there's a number 1, 2, 3, and 4 up above each one of the datagrams. So each datagram is a word with a header on it there. And so datagram 1 goes into the cloud down below there, the pink cloud with all the switches, and it follows any path that is available at that point in time to get to its destination. Then packet 2, or datagram 2, gets put on there, and it follows its path. And it probably is not the same path that data 1 took. And then 3 gets thrown on, and 4 gets thrown on. And so all these packets get thrown into the cloud, and they just kind of haphazardly, and obviously it's not haphazardly, it's very organized by microprocessor circuitry. It's a very sophisticated process, actually. But the point is that they don't have to follow a single path. They don't have to all go down the same collection of circuits there. And so eventually they do come out the other side of the cloud to the destination, and based on the sequence number, they're all eventually going to be put back into order. But you notice they do come out of the cloud out of order because they went through the cloud at a different, choosing different pathways, and so that affected their speed at which they got to the destination. So you see 2 came out of the cloud first, followed by 1, followed by 4, followed by 3. So that's part of what the packet assembler disassembler does now, is it receives those incoming datagrams, packets, and it reads the sequence number and puts them all back into the correct order. And so now as it comes out of that bottom pad, you'll see that the whole message is now back in its order. All the headers have been stripped off as well, and so then it's being passed to the modem and back to the receiving computer there, and of course on its screen appears the message that was sent by the sender. Now there's 2 different ways of sending messages between devices and through those clouds, like we were just looking at in the previous slide there. There's the connectionless method and there's the connection-oriented method. So in the connectionless method, we just kind of throw the data out there and hope it gets to its destination. And it's not an absolute necessity that the message does get to its destination, because more than likely, depending on the scenario, but more than likely it's going to be repeated time and time again until it does eventually get to its destination. In a connection-oriented network, we actually set up a connection first between the sending and receiving device before we ever transmit any data. And there's some error checking going on there that helps with the reliability and whatnot. So the table down below just kind of compares these 2 methods, connectionless to connection-oriented. So with connectionless, there's not as many headers that are placed on the datagrams, the packets, so there's a lot less overhead. Whereas connection-oriented, we have more headers, so there's more overhead, meaning there's more bits that have to travel to make the thing work. You have to do the setup of the connection too. So just setting up the connection creates a certain amount of overhead. In other words, a certain amount of, a number of bits have to be utilized just to set up the connection that don't really transmit the message that wants to be sent between the 2 devices. The greatest strength of connectionless is its ability to dynamically reroute data. The greatest strength of connection-oriented is its reliability. And connectionless, there is no call setup, so that's why it's called connectionless. There's no pre-established connection that's made. That's is referred to as a call setup. Whereas connection-oriented, then yes, there is a call setup. So that's what I was saying before, that this whole connection between point A and point B has to be established before any messaging is going to be transmitted. With connectionless, they use global addressing, whereas connection-oriented, they use what are called local logical channel numbers. Connectionless is also known as datagrams, unreliable. Connection-oriented, referred to as reliable virtual circuits. The error correction on connectionless is left by the end user devices. Multicasting is kind of a good example of connectionless, where multicasting, they just send streams of video bits out to the destination there, and so the receiving end has to calculate whether or not it's receiving it in a timely manner and make adjustments accordingly. Connection-oriented uses error correction within what is called the virtual circuit, and also the flow control, which means the speed at which the data is sent and received at both ends is left to the end user devices in connectionless, and is by virtual circuit in the connection-oriented method. To finish up this chapter, we'll be taking a look at error control techniques. So we'll be taking a look at error prevention, error detection, error correction, and flow control. Error prevention means that we're just trying to prevent errors from occurring in the first place. Some of the things that cause errors are noise and electromagnetic interference on the lines, and so there are several different things that we can use to improve what is called the signal to noise ratio. So the stronger our signal is to this interference, then the more likely it is that that signal will be received and processed correctly. So we use things like filters, amplifiers to increase the signal, also repeaters, because after the signal travels for a certain distance it begins to get weaker and weaker, and the signal to noise ratio is reduced quite a bit. And so we can take a repeater and have it take an incoming signal, and it retimes it, regenerates it, and puts it back out onto the media again as a nice, clean, fresh new signal. So 3 different methods then of improving the signal to noise ratio, again trying to prevent these errors from occurring. We also have adaptive protocols where the transmission speed is adjusted based on the error rates. And so these adaptive protocols allow us to increase the transmission speed, send more and more bits as long as there aren't any errors occurring. But then as soon as errors start to occur, because it's an adaptive protocol, it recognizes that and it starts to slow down the transmission a little bit, so we get back to a speed that is more conducive to the conditions that we're currently operating under. So it could be, you had an electrical storm move into the area while you're in the middle of transmission, and so that's going to generate more noise or interference on the wire and interfere with the signal, and so cause more errors. And so the adaptive protocol can recognize that and reduce the transmission speed to make sure that it's more error-free. Error detection is exactly that, the ability by the receiving device to determine that there has been an error in the transmission. So it detects the fact that it receives this message that's been somehow modified incorrectly in transmission due to interference or however that problem was caused. So for this to work, the transmitting and the receiving device need to both agree on how the error checking is to be calculated. So that's based on the equipment that's used at the sending and the receiving end. The transmitting device calculates and transmits the error check along with the transmitted data. So later on we'll be taking a look at data link frames, and data link frames use CRC, cyclic redundancy checks, in there. In fact, we're going to look at several error detection methods here in just a little bit. But the whole idea is that the error checking information actually is encapsulated in the sending frame, the frame that's being sent, and then it's recalculated on the receiving end, and that's how the receiving end can determine whether or not there is some sort of an error in transmission that has occurred. So that's essentially what we're going to go through here now, is just look at some of these error detection methods, and you'll see that we start out with a very simplistic type of error detection and we go to much more sophisticated error detection methods. So before we get to the error detection methods, this is just a quick graphic to show you the error detection process that I was just describing to you. So we have the sending machine on the left here. It's doing in the process of creating the message, it's creating the calculated error checking information. And essentially what it is just a mathematical process. It takes the data that it's about to send, runs a mathematical process, an algorithm on that data, and it comes up with a result. So it inserts its result in addition to that message within the frame it's about ready to transmit. So then it goes ahead and it transmits the frame. The frame travels through the public switch telephone network there. Gets received on the other end. The receiving end now goes ahead and takes the received data, and it also runs that same algorithm on the message and compares its results to the value that was stored in the frame by the sender. If they match, then that means that there was no error in transmission, and so then it goes ahead and continues to process the message. If it didn't match, then that would indicate that an error had occurred in transmission. So here are our 4 types of error detection techniques that we're going to take a look at. Parity checking, or vertical redundancy check, LRC, longitudinal redundancy checks, checksums, and CRCs, cyclic redundancy checks. So we start with parity checking, also known as VRC or vertical redundancy checking. This is the simplest error detection technique, and so thereby it requires less processor power. It's cheaper, more affordable. Parity works by adding an error checking bit to the end of each character as it sends it. So we'll see that in the next slide. Okay, so this is how parity checking works. This is the letter A again that we're going to be transmitting. And there's two different types of parity, by the way. There's odd and even, so we show you both examples here. There's odd parity and even parity. Both ends need to know that they're using a particular type of parity. So the sending end and the receiving end both need to agree that they're using odd parity or even parity. So let's take a look at the odd example here. The pink bits are the bits that make up the letter A. Remember in our previous example when we're talking about ASCII, the 7 bits are numeric 65 here to represent the capital letter A on the keyboard. So in odd, what we want to do is when we add up all the bits, we want to end up with a result that's odd. So if we just added up the pink bits, we come up with the number 2, which is even. So the parity bit, the one bit that's getting added here for the error checking, it needs to make our addition come out odd. So that's why we add a 1 as the parity bit, so that now when we add up all the bits, the end result is odd. Even, same thing, except that now we want to end up with an even number. So again, the pink bits, when we add them all up, they do add up to an even value. So that white box there, the parity bit that we add on the end, is going to be 0, so that when we add up all of the 8 bits, it comes out to be even. So the simple idea here is that for each character that's being sent, a parity bit is added on the receiving end. If the receiving end says that we're using odd parity, then I expect all 8 bits, every time I receive a sequence of 8 bits, it's always going to add up to be an odd value. If we're using even parity, then each sequence of 8 bits should always end up being an even value. So this is a very simple parity checking method, also known as vertical redundancy check or VRC, but not a real efficient way. And I'll show you in the next slide that it's very prone to error. So here we are again. We're still looking at parity checking, but you'll see now that when we have multiple bit errors, that's where we run into a problem with parity checking. So in the top example, just showing you again what even parity is all about. We add a 0 at the end. There's the parity bit, so when we add up all the bits, it comes out even. Now at the second example, what happens is during transmission, 2 of the bits get altered. So when we look at the pink block right now, that number that's the way the bits are set up there, that actually represents now the letter capital Q instead of our original letter that we want to be sending, which is the letter A, the capital letter A. So again, we had the 1 0 0 0 0 0 1 sequence is the character we were sending, but during transmission it turned out to be 1 0 0 0 1 0 1. Not only that, but the parity bit that was originally 0 now has been altered to be a 1 during the transmission. So on the receiving end, the receiving device adds up all the bits and says, well, that's 4. 4 is an even number. We're using even parity. There must not have been an error. So the Q is the letter I should think I should be receiving, when A was the letter it should have been receiving. So that's the problem with parity, is that it's simple and it's very cost efficient. It's cheap to produce, but it's not real efficient when it comes to multiple errors. If you have more than 2 bits that change on you, then obviously that's problematic. So we'll take a look at another more sophisticated parity method, or error checking method I should say, in the next slide. So now we're going to take a look at LRC, longitudinal redundancy checks, and it's devised to overcome the weakness we just saw in the previous parity checking method, what they call the one-directional parity checking. LRC adds a second dimension to the parity checking, and we'll see that visually here in the next slide. So here we can see how LRC works. Each of the 7 bits is organized into rows. So we have the vertical redundancy check, or the parity bit checking that we saw in our first example, is occurring horizontally here across each of the rows. And we're using even parity for the row check there. But then also vertically, each of the bits are being calculated as well. So you can see at the very bottom there, again, we're using even checking. And so there's an additional LRC row, so an additional 7 bits that are being added there. And then at the intersection of the VRC and the LRC, you'll see also that there's a bit added there as well. So that helps to improve the error detection capability of the device when there are multiple bit errors during transmission. Next, we take a look at checksums. These are block-oriented error detection methods as well, and get added to the block of data characters. The checksum is calculated by adding the decimal values of all the characters that are being sent, and then doing a division on it, and whatever the remainder is of the division process, that becomes the checksum that gets sent along with the block of characters. So this takes you through checksum in a little bit greater detail, shows you the actual checksum calculation. So again, we would take the block of characters that we're sending, and we would add the ASCII decimal value of all of those characters. We divide by 255. The remainder then is the checksum. So when we divide in, we're not going to get an even number. Whatever's left over, right, that's the remainder. And that becomes the checksum character then that's going to be transmitted. So if we have 128 letters that are A's that are being transmitted, that's the calculation that we're showing you here. So remember that the decimal value of a capital letter A is 65. We're to transmit 128 of those. So we would take the value of the letter A, multiply it by 128, which comes to 8,320, divide that by 255, which is going to be equal to 32, and the remainder is 160. Now 160 is translated into binary, which you see there at the very bottom of the screen, 10100000, and so that would be the value then that gets added to the block of characters that are being sent to the recipient. The recipient then again would do the exact same mathematical calculation, and as long as it came up with the same result, 160 as the remainder, then it would know that there's no error in transmission. The most sophisticated error detection method is the CRC, or the cyclic redundancy check. This is the same one that we use at the data link layer in Ethernet networks. And CRC uses binary division. There's 2 types of CRC, 16-bit CRC, which uses 17 as a divisor, uses a 17-bit divisor I should say, and 32-bit CRC, which uses a 33-bit divisor. So in each case it uses one more bit than the actual method or type of CRC that's being utilized. So error bursts, so errors that occur up to 1 bit less than the CRC, meaning 32 bits or 62 bits, depending on which we're using, can be detected 100% of the time. Larger error bursts at 100% minus half of the CRC, so 32-bit would be, half of that would be 16, 100 minus 16, 84, or 16-bit would be 8, so 100 minus 8, 92. That would represent the percent of time that errors could be detected. So it's a very sophisticated, very high rate of error detection method. So we've looked at error prevention, error detection, and now we're going to take a look at error correction. So the whole idea of error correction is that once the device, the receiving device, detects that there is an error, it's going to request a retransmission. The sending device then retransmits the portion that contained the error. And the error correction protocol, its sophistication is based on how the transmission is requested, how much data needs to be retransmitted, and how retransmission time is minimized. So these are the three criteria that we look at in the protocols that we're going to discuss here. And the protocols that have more of each of these three methods here is the more sophisticated method. The better way to go. So our error correction methods are known as ARQs, or automatic retransmission requests. There's three different types. We have discrete ARQ, which uses acknowledgments and null acknowledgments. We have continuous ARQ, and we have selective ARQ. In discrete ARQ, also known as stop and wait, the receiver sends an acknowledgment, known as an ACK, if no errors are detected, and the receiver will send a negative acknowledgment, or NACK, if errors are detected. So if the sender receives an ACK, then it sends the next block of data. So an acknowledgment says we got everything okay, no errors, so the sender says, all right, then I'll send you the next block. But if the sender receives a null negative acknowledgment, a NACK, then it will retransmit the original block. Continuous ARQ eliminates the need for the sender to wait for an ACK or a NACK to be sent back to it. This one's also known as the sliding window protocol. The idea is that the sender includes a sequence number in each block of data that it sends out. The receiver then only sends negative acknowledgments when an error is detected, and in addition it returns the sequence number that was an error. So once the sender gets a NACK back from the receiver, the sender will identify which sequence number was in error, and it will slide back to that number and then begin retransmitting the message at that point. With selective ARQ, this is the most efficient of the three when compared to the continuous ARQ, which retransmits from the point of error. So just say that there was 100 sequences of messages that got sent out there, and a NACK was sent back at sequence number 80. Well, the sender then would slide back to sequence number 80 and then retransmit 80, 81, all the way back up to 100 again. In selective ARQ, only the sequence number of the sequence that was in error is what is retransmitted. So in that same example, say you've got 100 sequences being sent. The sequence number 80 was in error on the recipient's end. So the receiver sends a NACK back with 80 identified as the sequence that was in error, and at that time the original sender only retransmits sequence number 80 instead of all of the sequences from 80 back up to 100. So obviously a much more efficient method of error correction. And finally we get to flow control. Flow control is the method between the two communicating devices that they use for identifying how well they're able to process the data. So if one device is overwhelming another device with the data that it's sending to it, then the receiving device that's being overwhelmed could communicate back to that sending device and say, hey, slow down, you're sending me more data than I can process. So it's basically designed to prevent buffer overflows that the receiving device might achieve, and it just sends a signal back, as I said, to the sending device to help alleviate that problem. The flow control software is constantly monitoring the amount of free space that's available in the buffer memory, and it tells the sending device to stop sending data when there's insufficient storage space for what it's receiving. And when the buffer is freed up again, there's more room to receive data, then it will send a signal back to the sending device and tell it to go ahead and resume transmitting. So that's it for the end of Chapter 2. We'll talk to you again next in Chapter 3.